Okay, so we now start chapter 1 of the book and the actual lecture, which is about definitions and statements. So what I'm trying to say here is we're not going to look at proofs today. We're only going to look at Lean as a language in which one can define functions and state properties about those functions. So basically a functional programming language which with a capability of stating properties. So first here you see the first lines of Lean. Just ignore them. They're part of the setup that we need to have better pretty printing. We open the namespace love. Again, you can ignore this for now. This is just to avoid problems later with duplicate names. So one way to look at Lean is as the equation Lean equals functional programming plus logic. So if you have experience with Haskell, OCaml, or even Scala, then you can think, okay, this is the functional programming part here, and what we're adding is logic in the form of quantifiers, right? For all, exists, and also connectives, and, or, and so on. And today we're going to cover types, recursive functions, and lemma statements, as I said. So those parts is what we have in functional programming, and the lemma statements is where the logic comes into play. Now, this course has functional programming more or less as a prerequisite, but we don't enforce it strictly because sometimes you have mathematicians who pick it up quite quickly. It feels quite natural to them because it's similar to universal algebra. And also sometimes you have computer scientists who pick it up very quickly by just reading a tutorial. And here's an excellent tutorial. It's a Learn You a Haskell for Great Good, exclamation mark. And make sure to read. It's the first 5 or 6 chapters, I think, but it depends which version. I mean, HTML or PDF. So just keep on reading until you hit the lambdas, and then read the lambdas as well. Okay. So now I'm going to assume that you have some familiarity with that material, or at least with the lambda calculus, which is the basis of functional programming. If you don't have that familiarity, then the current introduction is probably going to be quite rough, but I'm still starting from scratch. I will define everything I introduce. Right, so first we have types. So before we can have terms, we need a notion of types, which is a kind of universe, a kind of set in which the values can live, right? The natural numbers might be a type, whereas 1, 2, 3 might be values of that type. And we'll use Greek letters sigma, tau, epsilon to represent types. And there are 3 ways to construct types. So you can have a type variable, right, which is typically a Greek letter like alpha. You can have a basic type, so that's a fixed type. It's not a variable, and here I called it t. But that in real life it would be, say, the natural numbers or the reals or the booleans. And then you have complex types, which take arguments. So these are types that take other types as arguments, and they're just written with spaces in between. So you can have a list of natural numbers, for example, by just putting the word list next to the word nat for natural numbers. Again, this is a bit theoretical. We'll see examples further below. And then some constructors are written in fix instead of prefix, right? So this is a prefix syntax. You put the type constructor at the front, but with the function arrow, we put it in the middle, right? If you have a function from natural to natural numbers, you just put nat, arrow, nat. And the function arrow, just like in functional programming language, is right associative. So when you have a function with this type, this is really a function that takes a value of sigma 1 and returns all the rest here. I mean, you see it with the parentheses on the right, which in turn is a function that takes a sigma 2 and so on. And this is called currying, what we're seeing there, the fact that functions return functions. And if you haven't heard of currying, again, then I really would encourage you to read the Haskell tutorial. So Haskell has a slightly different syntax to Lean, but it's close enough that you will not be confused. So you will not waste time by learning some Haskell for great good. And here I mentioned polymorphic types. These are types that have type variables in there. So that's, think of the generics of Java, for example, or the templates of C++. So sometimes you want to have a function that you can instantiate with, you know, different types, and that's achieved with the type variable, but then you also need this prefix. So for the moment, don't worry too much about it. All of this will come back several times during the course. Okay, so those were the types. And then once we have the types, we can build the terms. And the terms, there are only 4 ways of building them. You can have a constant. So what we call a constant is really, it's almost everything, right? So when you have sign in mathematics, we would call that a constant, you know? So any function or any, so pi is a constant, right? So whether it takes arguments or not, we call it a constant. A variable is something you can instantiate, right? You can say if x equals 1, right? Application, this is function application. And again, it's written in the style of functional programming. So no parentheses, no commas, nothing. So when you want to, I mean, here you have an example of an application. You apply f to x, y, z. So 3 arguments, no parentheses, no commas. So that feels very strange at first, but you have to get used to this as fast as possible because the whole course rests on this. So if you're in lecture 5 and you're still confused about that, I can already predict that things are not going to go well at the exam. Okay? And then you have lambda expressions. And lambda expression has a weird syntax, lambda x comma t. Notice the comma, it's not a period like in other systems. And what it means really is this. So mathematicians would write this version here. X maps to t, where t is an arbitrary term. For example, x maps to x plus x, right? But for some historical reason, we don't use this nice mathematical notation. We use the Greek letter lambda for anonymous functions. But they're really not, they shouldn't be scary. They're really just functions. You don't want to give them a name, so you define them in place. And I think most programming languages in the meantime, including Java and C, I think even, at least C++, have lambdas, Python, and so on. So I mentioned currying earlier, so here it comes back. So currying is the idea that you can apply functions to various number of arguments. So if you have a function f that can take up to 3 arguments, you can supply all 3 arguments, or you can supply just 1 or 2, or leave it completely unapplied. And this is fine, right? It gives you another function, right? So f just gives itself, and f of x gives a binary function which, you know, has the same behavior as f, except, you know, always with x as the first argument. And application is left associative. That means when you write this, you actually, in terms of parentheses, are writing the thing there. You apply f to x, you get a new function out of this. You apply that new function to y, get the new function, apply it to z. But most of the time, we don't think of it as a chain of function applications. We just think of, okay, we just applied f to 3 arguments here. Even though in principle, application is always unary, strictly speaking, right? We saw it earlier. The application here is unary. You have 1 argument at a time. Okay, now we come to the examples, finally. So the check command of leen can be used to check the type, or just to, I cannot just enter n here, it would be syntactically incorrect, but I can tell leen, oh, check that n is really something. And it tells me, oh yeah, this is syntactic sugar for NAT, N-A-T, and it has type big type, so big T type. So basically natural numbers are a type, integers are a type, empty is a type that has no elements, unit is a type that has 1 element, bool has 2 elements, and then you see you can use a function arrow to build complicated types, right? So this one, and notice you can even learn how to enter this in the editor just by hovering over it. But there's also another way to do it is by going to the Hitchhiker's Guide, and at the end of the preface, there's a cheat sheet with all the symbols you're going to need there. So right before chapter 1. Okay, so yeah, you see function that takes 2 arguments, curried of course, and returns a third one. This one here takes a single argument, which is a function. This one takes 2 arguments. The second argument is a function. Okay, now we get into lambda territory. So this is a function lambda xx, where the x has type n. So I can remove that. So I can say, okay, this is the identity function. It takes its argument and returns it unchanged. This is the same thing, but here I'm more precise. I'm telling Lean I want it to work only for natural numbers. So it gives it a more precise type. Now, this is a more complicated one where we have a whole bunch of lambdas at the front, and then we finally have what we're trying to do here. So we're saying, well, we have x, we apply f to x, g to the result, and h to the result. And then we take all of these things as arguments with the right types, f, g, h, and x. And then Lean checks that this all has the right type. So if I remove h here, it would complain, right? So at the bottom here, it says function h has type blah. So the error messages are not always very readable. You really have to use your brain in such situations, unfortunately. But this is good. This is a university, so maybe it's not that bad. Here's the exact same thing, but with a more concise format. So I decided not to repeat the lambda. I just put the lambda once at the top here as the only lambda. Then I realized these 3 FGH have the same type. So I'll factor them like this, and X has a different type. So this is just syntactic sugar. To Lean, these 2 lines are exactly the same thing. And in fact, if you look at the bottom of the screen, they're displayed in the same way. And we even see what's the type of the resulting expression, right? Okay, so next we declare some constants. So that introduces fixed constants with no interpretation, no meaning. So we just say let a and b be integers. Let f be a function from integer to integer, and let g be a function that takes 2 integers and returns an integer. Right? This is what constants says in mathematics. And then we can use them, and this time, well, we don't need to put lambdas, right? We get them directly from the context. There's only x that's not declared, right? So these are other examples that are maybe more realistic in some sense. Typically, we have some constants lying around that we can use. And here's the identity function again. And we see it has a kind of weird wildcard type instead of just not like we had above. So we don't want to go that route now. And finally, here I introduce a constant, which is a type. So even types are constants, right? And I call it like natural numbers, not is also a constant. Everything is a constant, every identifier, I guess. So here I call it true because it's a 3-valued Boolean, so it's a portmanteau word. And I declare 3 values of type true, right? True, false, and maybe. And I put them a little prefix because we already have some trues and some false lying around, so it's better to keep them in their own namespace, right? So far, so good. So we've seen a bit of type checking implicitly, right? Because we've changed an expression and then the type was not correct. But what are the rules used by Lean to check the types? And and how does one specify those rules? Well, of course, we could look at the source code of Lean and try to infer the rules from there, but that would be very complicated. So instead, we use what is typically called a type or typing judgment. It's a formalism that, if you're not familiar with it, might look a bit strange at first, but it's very convenient, and we're going to use it over and over in this course. So these big horizontal bars, so rules with big horizontal bars. These are called formal systems. So if you look on Wikipedia for formal systems, you'll see a nice little introduction, which I recommend to the whole, to the whole mechanism. And we're going to see them over and over in this course. Okay. So the idea is that first you define a judgment, which is in some sense a statement of something. In this case, T has type sigma. in a local context C. So the important part is really T has type sigma, but you're allowed to make some assumptions. You're allowed to have a local context that says, oh, I'm under a bound variable called X, which has type nat. So I'm allowed to refer to X, right? So that's why we have this third argument. And if you wonder, why is there this strange symbol here and what does it mean, right? Or how to type it, well, there's the answer. And a column, well, don't worry, this type judgment is just a triple, right? It's a triple that contains C, T, and sigma, and then it has a very strange syntax just because historically this is how we write typing judgments. But it really just bundles three things together. Okay? And these are the typing judgments now, at least the simplified version. So for the simply typed lambda calculus, so for a fragment of lean, but for the moment that will be enough. And we see the first, we have four cases. You remember when we created the terms a bit upstairs, there were four ways of creating terms. We could have a constant, a variable, an application, or a lambda expression. And here the typing rules actually fit, there's a one-to-one correspondence with that. It's not always the case, but in this case, we have exactly as many rules as we have ways of constructing the terms, so that makes things easier. And so this is, let's look at one rule, right? So there's a bar. Everything above the bar, these are the assumptions that you make, the premises, the things that must be derived before you can derive the conclusion, the prerequisites. And here there are no prerequisites. This is we sometimes call this an axiom. This is something you can just apply without asking questions, except that there's a side condition here, which must be met. And the rule has a name, which is convenient, but the name has no particular meaning. It's just a convenient label. So here, if C is declared, globally with type sigma, just like we declared A and B earlier with type nat, then we're allowed to derive this for any local context. We actually don't care about the local context at this point. It works globally, it works locally. It's completely unrestricted, but the C and the sigma must be in the relationship highlighted here. For variables, we have a similar situation, except that variables we don't expect to come from the global context. We expect to come from the local context here, which is explicitly captured by the judgment, right? So here we expect X with type sigma to syntactically occur as one of the elements of the context. And the context is typically a list. So you just look, it's one of the entries of the list, that. Right? For applications, things get quite exciting because we have two premises and one conclusion. So, so if you're able to type T with this type, sigma to tau, a function type, and you manage to type U with the type sigma, which is the type of the argument here, then you can pass U to T, right? And you get something of type tau, right? Which is the result type of the function. This one, I think you might need to look at it a bit and play a bit with it. When I say play with it, I mean instantiate it, replace C by the empty list, replace T by a term like, I don't know, F or sign, replace U by 5, replace sigma by nat, and replace tau by int or something like that, and then see how the rule works. So many people understand rules better when they look at concrete examples, right? Not the rules with lots of meta variables like we have here. And then finally, we have the lambda rule, which is exciting because this one is better read bottom up, right? So we want to type a lambda with, obviously a lambda will be a function, so it's going to have to be sigma to tau. And the sigma is going to be the type of the bound variable. So far, so good. So how can we do this? Well, we have to be able to type T with the type tau, which is the result type. So the result of the lambda has to have the right result type. So that explains this part, and the C is here, so that explains that part. But then the question is, what is that? Why do we enrich the context when we go up? And actually, it's because T is allowed to refer to X, right? You're inside, I mean, when you're in T, you're allowed to refer to the bound variable. So when you try to type T here, you should be allowed to refer to X as well. But now the lambda is gone. So we simulate it or fake it by putting it in the context. So the X that was there is now in the context. Okay, and finally, I want to mention a related question to type checking, which is that of type inhabitation. So now we have our type system. We know what, everything we can type with the type system is correct, well typed, and everything else is not. But the problem of type inhabitation is you have a type and you wonder, is there a term that has that type? Is there an inhabitant, we call it, of the type, right? For example, the empty type we saw earlier doesn't have any inhabitants, whereas the Boolean type has true and false as its inhabitants. And here I'm going to show how to do it, because this is where the puzzle, or rather the video game aspect of the lecture already comes into play. So I'm going to remove the answer here, and I'm going to apply a certain procedure which is described right above, and also in the Hitchhiker's Guide. So we are asked to find a term which has this type, right? We're defining a symbol, some fun of type, which has this type, and then we have to provide the definition. So we have to find a term. And how do we do that? Well, the procedure says if the type, which is in this case, the whole thing here, is a function, and here it is. It's a function from this part here to there. And it's very important to be able to locate the functions and find out, okay, I have to take the left one, not the right one, because arrows are right associatives. It's important to, in general, to be able to find the root symbol of an expression, to imagine any expression, a term, a type, as an abstract syntax tree, and to find, okay, what is the root of the whole thing? And this here is the root, and then you have the left-hand side, which is tau in the instructions above, and you have the right-hand side, which is epsilon. And then it says, well, if it's a function type, then an inhabitant will start with a lambda. And what do we call it? Should we say lambda? So it says lambda x comma underscore. So the underscore is some kind of placeholder that, it means the whole expression will be syntactically correct. You see, if I leave it, then it waits for more and probably gives errors further down. We don't want that. We want our expressions to remain syntactically correct as much as possible, but it warns you here that, oh, there's a hole here that you should fill. Now I'll change the name here. It's a binary function. I'll call it G. That's quite natural. And then I keep on going. By hovering over the hole, it tells me what it wants, right? Now we want to synthesize this type here, which is again a function type. And the argument is this thing here, which is a unary function. So I'm going to call it f. So I put lambda f here, and I put the hole again. Again, using step number 1 of the procedure above. This I can ignore. So it's just, and then, okay, another function again from alpha. So, okay, a value of type alpha. What's a good name for it? A. A is a good name. Please use A, actually. Please try to use good names. That really helps grading, and also I think it helps you. And then finally, we have to provide a gamma. And okay, and now a gamma is not a function, so we probably have to use step 2 of the recursive procedure. And that says, go in your context, what you have here, and look at what you have and see if there's something that ends with gamma, like here, right? The others don't end with gamma. That means you can use G. But to use G, you need 2 arguments, which we don't have yet. So we're going to put placeholders for the arguments. So we're going to put G, tuck, tuck, right? And then we're getting closer. I wonder what this error is. Oh, that doesn't matter. Okay. And now, now we have two holes. We go recursively. So we need to fill an alpha. We have an alpha just by taking A. We don't need to do anything else. So this is great. So I'm just putting A here. And then here, it needs a beta, and the beta is provided by F, and it takes one, F takes one argument. So I'm going to write F of something. Then we continue. What's the problem now? This time is beta to alpha. We have a function. So we're back to rule 1, right? So we're going to write a lambda. B will be a good name because it's of type beta. And now we need an A, and that's great because an alpha, because we have A. So we're going to put A. And that's it. That's how we do it. And notice at all times I made sure that my program would at least compile. And this is a really good rule of thumb. Also when you do programming in the wild, in Java, whatever language, don't start doing big refactorings and then your code doesn't compile for 3 weeks. It's never a good idea. Do it step by step and make sure that it compiles, you know, every minute or every hour, or, you know, as much as possible. And that is especially true when you deal with functional programming and with proving. And now you will wonder, why have we played this silly exercise of trying to inhabit a type? Well, it turns out theorem proving is extremely similar to what we've just done, except that the arrows will mean implications, roughly. And the lambdas or lambda g's, those will be assumptions. But we'll come back to this. But all I want to say is, you know, this is like in Karate Kid, you know, movie you probably haven't grown up with, but where the sensei was teaching this kid karate, and the way he was doing it was having the kid do all these chores, like, you know, waxing in, waxing out the car, waxing, and the kid was just very annoyed because he wanted to learn karate, not, you know, do all the household work of his sensei. But in the end, he became a really good karate kid because he followed these instructions. So, well, I am your sensei. I'm telling you, inhabit your types.